Tuan, I got to know from Yoshi Tagawa told about your study, and I'm very impressed with the series of study, your series study.
Okay.
That's why I got to know you.
Oh, thank you. Yeah. So Yoshi was my office mate actually in the 90s.
Oh, yeah.
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 So we worked together in the same lab.
Oh, great.
Yeah, yeah.
He's a very nice guy.
Yeah.
He
I
was
visited
former.
him many times in Japan.
Oh, so you should come
Yeah.
to our lab. Could you please show up there? Could you please visit our lab the next time when you have a chance to come to Tokyo?
Yeah,
Yes,
that'd be
yes,
wonderful.
yes. Very welcome.
Yeah.
Very well. Yes, I'm happy to
Yeah,
invite
next time
you
I
for
think
the...
I'll visit Yoshi in somewhere in May. So
okay, great.
possible I'd like to swing by your lab.
Okay,
Yeah.
yes. There's a big conference for the March Space Flow, ICMF, in Kobe, in the beginning of May, in the beginning of April.
Okay. Okay.
So the abstract deadline has already passed, but there's a lot of people who, I think many of us will join the ICMF Kobe.
Oh, so
but
the
I'll
abstract
try to come, right?
Passed.
Ted, can you come, Ted?
I'm not sure yet.
Okay.
So, Tuan, just to remind you that Tally will mute everyone and turn off our videos. So please turn on your video and audio.
So my video is already on, right?
No,
but
it will be.
Before she starts, she will just to make sure that you are the only person with video on and audio on. Okay. Initially, I think Shu will be also having his video and audio on. He will introduce.
And then I will.
I'm going to admit everyone in. It's in minutes. So in the waiting room.
Okay, time to start maybe. Hello, everyone. Good morning, good afternoon, good evening, and good night. And my name is Shu Takagi, Professor Department of Mechanical Engineering from the University of Tokyo. And today we have a speaker from Singapore, Professor Tran. Let me introduce him shortly. Dr. Tran is an associate professor of the School of Mechanical and Aerospace Engineering, Nanyang Technical University, Singapore. He received his bachelor degree in engineering mechanics from the Hanoi University of Science, Vietnam in 2004. Then he pursued his graduate study, which focused on the thin film flows at turbulent frictional drag at the University of Illinois at Urbana-Champaign and USA. Upon completion of his PhD degree in 2010, he started working at the Physics of Fluids group at the University of Twente, the Netherlands, as a postdoctoral researcher. He joined Nanyang Technical University in 2013 as a Nanyang assistant professor. Tran's research encompasses a wide range of topics from complex mass phase flows and soft matters to application-oriented topics such as development of droplet and power-based 3D printing technology. So today he's going to talk about the impacting droplets on solid surfaces and mediation of entrapped air film using dielectrophoretic effect. So Professor Tran, please start.
All right. Thank you, Professor Shu, for your kind introduction. And hello, everybody. Thank you for joining us for our seminar today. So before I start, I'd like to thank the organizers of the International Journals of Multiphase Flows who have put together this seminar series and have given me these wonderful opportunities to share my work. I would also like to thank Professor Loze, Professor Prosperity, and Professor Sun, who worked closely with me and introduced me to this topic of droplet and surface interaction. And this is also where I did my postdoc in the Physical Fluids group in Twente. I'd like to thank my collaborators, Yoshi and Susanta, and various students and staff that I've been working with on these related topics over the years. In particular, I'd like to thank Kuo, who actually worked with me on the dielectrophoretic effect during his time in NTU. So finally, I'd like to acknowledge various funding agencies in Singapore who have supported my research work. All right, so let's start with the impacts of droplets on surfaces. So these surfaces, this phenomenon can be observed almost everywhere, and it also the one with the long history. So as early as 1876, Worthington, despite having no access to photographic means, used strobe light to instantaneously illuminate droplets impacting on flat surfaces and made sketches of impact patterns from his memory. So here I'm showing this his setup that can instantaneously spark light, and he would observe impacting droplets at different stages of the impact, and then would sketches the impact as shown in this this sketch here. Right. So over the years, with the development of illumination devices and high-speed cameras, we have been able to observe a lot of impact phenomena, both in nature and in technological application in great details. For example, in this movie, I'm showing a droplet impacting on a tiger moth wings with great details, and with the motion has been slowed down considerably, as shown in this movie. Other examples include impacting droplets on powder bed, which is very relevant to 3D printing technologies, or micro droplets ejected from micro nozzles, impacting on surfaces with high velocity. And eventually, if you look closely here, you can see a little bubble getting entrapped under the droplet. Another example is splats formed by molten nickel droplets at a very high velocity. All right. So one of the phenomena that is rather robust and consistently observed during impact of droplets is the early deformations of droplets before it actually touches the surface. So in these movies, I'm showing the side view and bottom interferometric view of a droplet coming into contact with the droplets. And as you can see, initially the droplets spread as if it spreads on a superhydrophobic surface. And the reason for that is because it's skate on or sustained on an air film that gets trapped between the droplets and the solid surface. And this air film can be visualized by bottom interferometric view. The air film eventually collapsed and may trap bubbles in under the droplets. All right. So let's take a look, a closer look at the early deformations and bubble entrapment of an impacting droplets on solid surface. So in this schematic here, I'm showing the droplet that is approaching a solid surface. And because the air has to be squeezed out in order for the droplet to touch the surface, so there will be a pressure buildup under the droplets. And eventually this pressure buildup is going to be large enough to deform the droplets and create these dimple formations. So the dimple formation can be visualized by interferometric high-speed camera recording. And the profile of the dimple can be extracted as I show in this movie here. All right. So we can see that the dimple is getting larger and larger in the lateral size, and the height of the dimple is getting decreased as the droplets moves closer to the surface. After the air droplet collapse, contact would be initiated between the liquid and the surface, and eventually the wetting motion is going to trap bubbles underneath the droplets, as shown in this movie here. Right. So the entrapped air film and the resulting bubbles are quite robust. They can be observed in various similar situations or systems. So for example, we could have a similar situation in which we have liquid coming into contact or solid liquid coming into contact. So in this snapshot here, we have a droplet coming into contact with a liquid surface. And because the droplet doesn't have a very high velocity, so it's going to come into interact with the liquid surface, and the air film between the droplet and the liquid surface is going to be able to sustain the weight of the droplets and does not rupture during the impact. So eventually the droplet is going to be bounced back, and the coalescence can be avoided until the air film is completely drained. In another situation shown down here, we have a droplet impacting on a surface fluid, surface bath, a liquid surface with higher velocity. And we can see, this is from the side bottom view, an air film is trapped, and eventually it gets ruptured between, and then we could observe here that various bubbles can be seen as a result of the air film ruptures. Eventually we have air film bubble trapped or immersed in the liquid. Another situation we could have is solid liquid contact, but in sort of a reverse way, which is that we have impact of solid spheres on a fluid bath. So this is also a side bottom view, and here we can observe that there is an air disk that get trapped under the solid spheres, and the air disk eventually would be contracted, and eventually a bubble is going to be created under the spheres. Right. So beside bubble entrapment, splash is another well-known phenomenon that can be observed during impact of droplets. The connection between entrapped air film and splashing was first brought to light by Su, Zhang, and Ego in 2005. So in this movie, I'm showing a droplet impacting on the solid surface in normal atmospheric conditions. And we can see a spectacular splash here. Right. Now, if we reduce the air pressure to 0.2 atm, then the splash is completely suppressed, right? So obviously there is a strong connection between the surrounding or the ambient air and the splash occurrence. Now, there are other studies attempting to link the splash phenomenon with the air, the ambient air. For example, in this sketch here, it was shown that the liquid skates on a very thin air layer, and this air layer can be as thin as tens of nanometers before it makes contact with the solid surface. And this event happens before splashing occurs. Recently, there is a recent model that was proposed to account for splashing, which essentially is the ejections of expanding lamella. And the force that is responsible for ejections of the lamella, it was shown in this study that basically is the combinations of lubrication force that occurs at the wedge that is sandwiched between the expanding lamella and the solid surface, and also the lift force on top of the expanding lamella. So if this combined force is larger than the capillary force that keeps the lamella from extending forward, then essentially the splash would occur. So one of the questions that people have been asking is with regards to the airfilm and the outcomes of the airfilm trap between droplets and surface, is how to suppress or enhance the trap airfilm and splash. Sorry, let me just remove this part away. And so one of the ways to minimize the volume of the trap bubble could be just by manipulating the impact conditions. So in this plot, I'm showing the dependence of the volume of the entrapped air on the inertia of impacting droplets. So basically, there are two effects that can minimize or reduce the volume of the entrapped bubble. One is by increasing inertia of the impacting droplets, and the other, on the other extreme, is by increasing the capillarities, which essentially is increasing the surface tensions of the droplet. Right. So between these two effects, by that work to minimize the volume of the entrapped bubbles, there is an optimum point of the two that is balancing between the two effects that basically work to maximize the volume of the trap bubble. So basically, by manipulating the impacting inertia or the capillarities of the droplet, we can control or have some sort of control over the volume of the trap bubble. Another way is to essentially to suppress splash is by letting it drain through channels that would be fabricated on solid surface. So here I'm showing the movie that of a droplet impacting on a smooth surface with a splash. Right, so this surface has no channels to drain air. Now, in another instance, we have air channels fabricated on the surface that would let air to drain out. So in this case, we would have splashing that occurs, suppression of splashing. Right, so completely suppressed for splashing. Another way to suppress splash is by using soft surfaces. So on the left movie here, I'm showing the impact of a droplet with 2.6 meters per second velocity and 0.88 millimeters in diameter in radius. So again, we are seeing a splash here. But if we are reducing the Young modulus of the surface down to 45 kilopascal by using silicon, then basically for the same impact conditions, we can see that the splash is greatly suppressed. Right. So, well, in opposite to diminishing the airfilm effect, in some situations, the effect of intervening gas phase can be enhanced. So, for example, we could have the famous line force effect in which the gas phase separating the droplet and the surface is continuously replenished by vaporizations. So in this movie, I'm showing a droplet impacting on a superheated surfaces. And because the vapors is continuously generated under the droplet, it prevents the droplet from touching the solid surface. Now, sometimes the effect of vapor flow under line force droplet can be quite fascinating. So for example, in the right-hand side movies, a droplet is deposited on a powder bed that is superheated. And this droplet can move by itself because of the fluidizations of the particles around the droplet it creates unstable pressure around the droplet that can push the droplet into one direction. So the drop can essentially sail on this powder bed. And this is one of the examples of the manifestations of the vapor film or the vapor flows under the droplet that could direct or generate some sort of motion for the droplet. So the question I'd like to ask in this talk is essentially how to manipulate the air film actively, given that the air film, the intervening air between the droplet and the surface has a very intricate and complex role in the outcome of the impact, such as bubble entrapment and splashing. So we can take a look at the air film that is trapped between the droplet and the surface. And basically, if we fix the interface between the solid and air, then the air film's thickness entirely depends on the interface between the air and the liquid. And one way we can use to control this interface is by the dielectrophoretic effect. This is one of the electrical effects that have been used very widely to control bubbles or droplets or particles in microfluidic applications for a long time now. So I'm gonna just briefly going through this effect and how to exert some sort of control over the interface using the dielectrophoretic force. So suppose we have an external field E, and we have the two media, one is liquid and the other one is air, with different dielectric constant. So for liquid, we have the dielectric constant epsilon, denoted as epsilon L, and the dielectric constant of air is epsilon A. Because of the induced charge on the surface, there would be a stress acting on the interface that we denote as sigma E here, that points along the directions of the unit vectors of the normal unit vector of the interface. So we can essentially derive in simple situation the dielectrophoretic stress on the interface between liquid and air as the following. In the air medium, we have the dielectric strength denoted as EA, and in the liquid medium, we have the electrical strength as EL. And these two electrical strengths are different because of the difference in the dielectric constants of the two media. So these two electrical strengths will still have to satisfy the boundary conditions at the liquid and air interface given here. If once we are able to get the expression for the electrical strength in the two media, liquid and air, then we can calculate the Maxwell stress tensor for the medium, for each medium. And essentially the dielectrophoretic stress at the liquid and air interface would be equal to the jump in the stress tensors multiplied with the normal vectors of the interface. So we have, in principle, these expressions that can be derived based on the electrical field that is in the liquid phase, right? So one thing I'd like to note here in this expression for the dielectrophoretic stress is that because epsilon L is larger than epsilon A, so typically this stress vector would point along the directions of the normal vector of the interface. And what it means is that the stress would be directed from the medium with higher dielectric constant to the medium with lower dielectric constant. And essentially it means that the stress would point in the directions from the liquid phase to the air phase toward the solid. Right. So in principle, we have a tool to essentially exert some sort of control over the liquid and air interface using the dielectrophoretic effect. The next step is to design a non-uniform electrical field in order to produce some sort of a outcome that we wanted, right? So in these examples, I'm using a interdigital electrodes as I show in this schematic here, right? So this interdigital electrodes is connected to a power supply that can supply the voltage U, and is electrically insulated from the liquid by a coating of thickness DC. The distance and the spacing between the electrodes are denoted as delta, and the substrate is transparent in the device that we have in order to allow optical access through the substrate, right? So basically we can see through wherever there's no electrodes here. So if we apply a voltage U across the electrodes, and we can essentially calculate the electrical potential inside the liquid phase if the liquid is at a constant distance h from the top of the coating surface, right? So in this formula here, this is the full Fourier expressions for the electrical potential inside the liquid phase. And the first order approximation is shown here. dP is the penetration depth of the electrical field, and in our experiments, it's roughly 32 microns. Right. So the first order approximations, when we apply the boundary conditions for the voltage applied on the electrodes, can be derived as these expressions. One thing I have to notice that this expression is valid for a large value of H. For small value of H, which means that when the liquid gets very close to the solid surface, then these expressions would need a correction factor. Right. So here I'm showing a simulated electrical potentials for the electrodes in our experiment. Right. So this is for the case that the liquid is 10 microns above the interdigital electrode substrate, and the applied voltage is 200 volts. The liquid is ethanol. Now, from the electrical potential, we can just take the derivative and or the gradient and get the electrical field inside the liquid phase. Right? This is again the simulated electrical field. For the case that the liquid surface is 10 microns above the interdigital electrodes, and the applied voltage is the same as the previous case. All right. So from the electrical field, basically we can calculate the dielectrophoretic stress, and this expression is the stress that is applying on a liquid surface that is parallel to the substrate, and at a constant distance h to the substrate. So the magnitude of the stress can be seen here, right? And as you can see, this is not a uniform stress. The stress, let's take a look at the blue line here. The stress is a nonlinear functions or periodic functions with respect to the lateral coordinate x. So when the liquid surface is far away, 50 microns from the surface, then the maximum point of the stress is at the center of the electrodes. Right? So as the liquid surface approach the solid surface, for example, if the liquid surface is 1 microns away from the solid surface, then the peak of the stress moves from the center of the electrodes to the edge of the electrodes. So this is where we have to apply a corrections to account for this change in the dielectrophoretic stress. So here I'm plotting the maximum value of the dielectrophoretic stress as a function of h for several values of u. And essentially, this is the stress that we can use to account for whatever the effect that would be induced by applying the dielectrophoretic effect. For small value of h, which means that when the liquid substrate getting very close to the solid surface, then we apply corrections for the dielectrophoretic stress. basically is a constant. All right. So let us see how the dielectrophoretic effect impacts the air films under the droplets. So in this experimental setup, this is a pretty standard experimental setup to look at the side view of the impact and also the bottom view of the impact using interferometry. So we have a coaxial light that looks at the substrate and the high-speed camera connected to a long-distance microscope. There is another synchronous high-speed camera to look at the view of the side view of the impact. And the droplet is induced from a needle that can be adjusted in terms of height to change the impact velocity. So using this experimental setup, we can have both views of the impact and look at the air films as the droplet impacting the solid surface, and as we induce a dielectrophoretic effect on the surface. So this is one representative photos or interferometric photo of the bottom view captured by high-speed camera. Here we have only partial view of the impact because part of the view is blocked by the electrodes. But in any case, we can essentially extract the profile of the air film using the interference film here. Right. So here I'm showing two examples of the dielectrophoretic effect. The first one is when we deactivate the dielectrophoretic effect. That means that we set the voltage to 0. And we have impacting droplets with moderate velocity and 1.3 millimeters in the radius. The snapshots here is taken at the same moment after initial deformation is detected. Right? So take a look at this first snapshot here. From this snapshot, we can essentially extract the profile of the air film on top of the solid surface, and the air film is extracted in two directions. The first one is along the y directions, and we can see that the air film along the y directions is roughly identical to the air film along the x direction, going through the center of the impact. So basically, the impact is completely isotropic, and there's no effect whatsoever. And this is very similar to normal impact on solid surface. Now, if we apply the dielectrophoretic effect, that means that we set the voltage to 250 volts. Then in the y directions, this is the air film profile. And in the x direction, we already see that there is already contact between the solid surface and the liquid. There's already wetted area along the edge of the electrodes here. Although, if we look at this channel here, where we can see the interference fringes, then the liquid has not touched along this line, along the center line in the x direction. So we can roughly reconstruct the air film profile along the gap of between two electrodes as the following. And this is the reconstructed air film profile for the air films that created the interference fringes along this gap here, right? So basically we still have a central dome or dimple, but this can be described as some sort of tunnels. Along this, the tunnels is directed along the edge of the electrodes, right? So there are two edges of the electrodes, one along this line and the other one along this line. And basically, as the droplet goes down, there is an airflow that is directed on the two sides of the channels, as I illustrated here. So the air film is ruptured along the electrode edge, but it does not rupture along this point or the end of the channels here. Between this point and this point, there's no rupture point. The air film only ruptures along the edge of the electrodes. So basically, the impact, the air film created under the droplet impact without the dielectrophoretic effect is very different for the air film created with the dielectrophoretic effect. So without the dielectrophoretic effects, the air film is basically can be seen as a flat disc, right? And eventually it's going to be rupture around the dimple. But with the dielectrophoretic effect, we can create channels that allows airflows, and basically these channels are the air film that get ruptures along this line, right? These are the lines of the edge of the electrodes. So this is some sort of a divide and conquer methods to drain the air that is trapped under impacting droplets. So we can see the effect of the dielectrophoretic effect when it works to eliminate bubble entrapment. So in these few movies, I'm showing the impact of droplets on the substrate with varying voltage, and this is the directions of increasing the voltage. So we can observe that wetting occurs sooner with higher voltage, and the entrapped air volume becomes smaller. Right? So the entrapped air volume is smallest for highest applied voltage here. So this effect is also quite robust in that if we change the impact velocity, we see a similar effect. That is, the volume of the entrapped droplets gets smaller and smaller for higher voltage. So we can quantify the entrapped volume of the air with increasing voltage in this plot here. So these few curves are obtained with different impact velocity, and we can see that the volume of the entrapped air reduces. All right, so in terms of splash, the dielectrophoretic effect also works in suppressing splash. So I'm showing here two movies, one without the dielectrophoretic effect and the other one with the dielectrophoretic effect. And apparently what we can observe is that there's no splash whatsoever when the dielectrophoretic effect is activated with the voltage around 300 volts. So we can take a closer look at how the splash changes with increasing voltage from the following snapshots. So all of these snapshots are taken for impacting droplets of the same radius and the same impacting velocity, and it's taken at the same duration after impact. So here is the splash without the dielectrophoretic effect, and we can see that the splash is pretty prominent here. If we increase the voltage to 40 and 80 and so on, we can see that the intensity of the splash is reduced, right? And at 160 volts, we can see that the lamella here is only has a few droplet that is disintegrated from the expanding lamella here. And splash is completely suppressed when the voltage is increased to 200 volts. So there is a threshold voltage to suppress splashing. So here we can ask questions: how does this threshold voltage changes with the velocity of the ejected lamella? This velocity is basically how it evaluates how fast the lamella expands, and we use this as a more convenient quantity instead of the impacting velocity of the droplet, because it's easier to use in our subsequent model. So we denote this expanding velocity of lamella as VL. So we can see that if we plot the splash behavior depending on the applied voltage and the expanding lamella velocity, then basically there are two regions mainly that can be observed. The one with splash and the other one without splash. And obviously there is a transition to splash between these two regions. Here I'd like to note that with the applied voltage being equal to 0, then this is the splash transitions without the dielectrophoretic effect, and the lamella velocity that transition to splash here is around 5 meters per second, and we denote this velocity as Vt. This is the transition to splash lamella velocity without dielectrophoretic effect. Right. So let's see how we can formulate a theory to account for the splash suppression defect using a force analysis for the ejected lamella. First, let's take a look at the expanding lamella without the dielectrophoretic effect. Expand lamella has a velocity VL, and basically the front of the lamella make a wedge with the angle alpha with the solid surface, and this wedge has the length L0 and the height H0. For this kind of lamella, there are two involving force. The first one is lubrication force that is created due to the moving wedge, and is created within the air phase under the expanding lamella. And it was shown that the lubrication force depends linearly on the expanding lamella's velocity, following this formula. Okay. Now the opposing force to the lubrication force is the capillary force, and basically this force works against the extensions of the lamella in the forward directions. So if the capillary force is larger than the lubrication force, then there will be no splash. And if the expanding velocity of the lamella VL is large enough, then the lamella would be ejected. So at the transition to splash, this is still without dielectrophoretic effect, then the capillary force is equal to the lubrication force, and the expanding lamella is equal to the velocity, the transition velocity to splash that we denoted as Vt. So basically, we can estimate the capillary force as KL eta A Vt, which is essentially the expression for the lubrication force, and with the lamella velocity being the threshold velocity of the lamella for splashing. Now, in the case with the dielectrophoretic effect, then we have an additional force, Fd here, which denotes the dielectrophoretic force. And this force basically is pulling the lower interface or lower surface of the lamella down. This force can be calculated from the dielectrophoretic stress by integrating the stress across the length of the wedge. Right? So basically, we have this expression for the dielectrophoretic force, and it's shown here that is proportional to the quadratic to the applied voltage to the second power. So for the case that the expanding velocity of the lamella VL is larger than the transitional velocity to splash, Vt, then the force pushing the lamella upward is the excess lubrication force. We assume that the capillary force remains the same because the geometries and the curvature of the lamella largely remains the same. So when we increase the expanding velocity of the lamella, only the lubrication force increase, and the dielectrophoretic force would have to work against the excess lubrication force in order for splash to be suppressed. So the condition to suppress splash with the dielectrophoretic effect would be that the dielectrophoretic force is greater or equal to the excess lubrication force. So we can solve for this solve for the applied voltage at which the splash is suppressed from the equation FD is equal to FL, and from which we can find the dependence of the applied voltage at the threshold as a function of the expanding lamella velocity. And if we compare with the experiments, then basically we have an agreement between the experiments and the theory that we derived earlier for the threshold velocity that can suppress splashing. All right, so I have come to my conclusion, which basically is that we have demonstrated and proposed and demonstrated a divine conquer methods using the dielectrophoretic methods that induces the control rupture of air film between the approaching surfaces. And with nowadays, the versatile electrode design and flexibility in the working liquids, this allow us to impose any rupturing patterns to the air film. And yeah, so thank you for tuning into my talk, and I'll be happy to answer any questions.
Thank you. Thank you very much. Very interesting. So, okay, so are there any questions or comments?
I have a question.
Yes, Bala, please.
Tran, a very interesting talk. Learned something that I never knew before. Thank you.
Thank
I
you.
have one question. These 150, 300, and 400 volts seems fairly large. Can you hear me first?
Yeah, I can hear you.
Yeah. So these voltages are pretty high. I mean, as a science, this is good, but I was just curious as to what you think are practical aspects of it in terms of power consumption, safety, and things like that. Do you have any comments on it?
Yeah, so the power consumptions and safety largely depends on the coating. If we have a very good coating, which here we use silicon nitride, then we wouldn't have any leaking and therefore current across the electrodes. And if the coating is not done very well, then we could also have burn out the electrodes. So in fact, it largely depends on the coating quality. Okay. If we have high quality of coatings, then essentially we don't need much power consumptions.
Okay.
So there's one question, the Jingwei, please.
Ted has a question.
Oh, Ted, okay, but also before the Ted, the person that yes, Jingwei, yes.
Good evening. Thank you for the very nice talk. My name is Jingzu. I'm from Tokyo University of Agriculture and Technology, working with Professor Yoshiki Tagawa. And I have questions about, because you're using a very high voltage here, does it affect the temperature of the surface? And I wonder whether it affects the interaction between the liquid and the surface as well. So yeah, what's your thoughts about that?
Okay, so honestly, we haven't measured the increase in temperatures of the surface. I don't think that there will be a significant effect because we don't have any current between electrodes, and the current is something that we can measure quite accurately in this experiment. So we monitor the current to monitor the leaking, and in the experiments that we did, there was no leaked current.
But does the temperature change because of the voltage, or if it changes?
I wouldn't think so. Without current, there would not be any power or any heat generated.
But I mean, if with the current, like for example, when it's 200 volts, does it change the temperature of the surface?
Having high voltage, as far as I understand, do not change the temperatures. So you could have kilovolts, and it's perfectly fine to touch. Yeah, as long as you don't have any current.
Okay, thank you so much.
Yeah.
Okay. So Ted, please.
So Tran, Chet Heindel from Iowa State University. This is a really interesting talk. All of your droplets appear to be quite small and uniform, or small and spherical. And I'm wondering, could this be expanded to larger droplets, or even like raindrops are non-spherical, and maybe not approaching normal to the surface?
Okay, so let me see if I understand your questions. You wanted to know whether smaller droplets can, or this effect can work with smaller droplets?
No, I'm interested in, will it work with larger droplets? And
Oh, okay.
Also, if those larger droplets are non-normal to the surface.
Yes, it does. It does. So the short answer is it does, and longer answer is that we actually have done experiments with in fact just a body of liquids on top of these electrodes, and yeah, it works in enhancing the wetting of the liquid on the surface. That is the overall effect.
Okay, thank you.
Yeah.
Okay. Are there any questions or comments? I have several questions. So I'm interested in the effect of the surfactant.
Oh,
If you have a surfactant in the liquid, what kind of phenomena do you expect? You have the earlier the suppression or the delay of the suppression with the adding the surfactant. Surface tension will be reduced.
So I think adding the surfactant would change the properties of the liquid bulk, which will come into in simple form would change the dielectric constants of the liquid, and also it would change the charge density on the interface as well. So I think, yeah, we haven't thought about that, but I think definitely it would probably has some effect on the stress on the interface.
Also, you have a reduction of the surface tension.
Yeah, also you have a reduction
Yeah,
in the
yeah.
surface
So
tension. Yeah, that is the first effect that is induced by the surfactants.
Will be interesting to see. But
yeah.
Lots of complicated, charge and the surface tension.
Yeah, definitely.
Okay, great. And how about the effect of it's not for the electric field, but how about the effect of the gas? If you change the species of the gas from the air to some other gas, the helium gas or the argon gas or some the CO2 or whatever that.
So I think changing the gas would essentially induce two effects. The first thing is that, well, in any case, changing the gas even without the dielectrophoretic effect would change the behavior of the impact because of the viscosity or the density of the gas that would change, right? So most directly will change the lubrication force that is acting on the lamella. So with the dielectrophoretic effect, I expect that it would change the dielectric constant of the gas. So it may change the stress as well.
Okay. So you said if you say the like lubrication effect, basically the viscosity of the gas will be important.
Yes.
But from the beginning, that if you think about the effect of the pressure, the reducing pressure, you don't have the
yeah. So the pressure would also affect the impact. I think there was a paper also discussing changing the gas phase that would induce different behaviors of impacting droplets and splashing. So they change various kind of inert gas to induce the behavioral change of impacting droplets.
Very interesting. How about if you have a small charged particles in the gas phase? It could be the possible, right? You have a very small, tiny particle, charged particle in the gas phase, and the electric field will affect charge, and that the gas is
Yeah.
easy to.
I guess. Well, in any case, the particles would be subjected to a net force because of the dielectrophoretic effect that acts on individual particles. I'm not sure how these particles are going to interact with the approaching liquid air interface, though. So I think that is something that is quite interesting to look at.
Also, maybe the wettability of the particle might be interesting to see that the wettable particle or the hydrophobic particle, then the duplication area, you might have some bridging effect, and that will affect the splashing the behavior. That will be very interesting to see.
Oh, that's right. That's right. Yeah. So we could use hydrophobic particles, for example.
Also,
so that it doesn't,
exactly. So you can check the effect of the hydrophobicity. Yes.
That's right. Yeah. Thanks. That's a very interesting idea. Yeah.
How about
I
the
guess
effect of
also, sorry.
Yeah, please.
Oh, well, I guess this is quite interesting because I also did a few experiments with, impacting droplets on powder. So this is definitely something that is worth trying.
And I'm very much interested in also the not only splashing, the control of the translation motion. You can control the translation motion by changing the asymmetric shape of the electrode, and so you can control the right. That will be also interesting to manipulate the small particle, also generating the transfer the droplet to some places. Transport the droplet to some places, then you might have the situation that you need to have some small splashing some location. So if you could manipulate the location of the particle by changing the electric field and the transfer the droplet to some the targeting point, and then by having some other type of the higher amplitude, if you can generate the splashing. So you can have the control of the droplet location, and also they can generate the small droplet coming out. That will be the from also heat transfer point of view. That will be very interesting to see the effectively cooling or something like that. Very interesting.
Okay, so we did some experiments with boiling as well to see the enhancement in the boiling with this effect, and we did see some sort of enhancement in boiling performance.
Very interesting. Okay, I gave a lot of questions. Thank you. Very interesting. So how about do you have another question or comments? Just feel free to. Okay, Bala, do you have some more?
Well, this is a great talk, different from several of the other talks that we heard. Tuan, thank you very much for a enlightening talk, and we will all meet in 2 weeks, right?
Yeah.
And that there's also one question.
Yeah.
I'm sorry.
Okay, thank you. You can ask.
Yeah. Have you tried changing the patterns of the electrodes on the surface, and then can you kind of move the electrons, move the droplets by changing the patterns of the electrodes or something like that?
I haven't, to be honest, because we are still working on the fabrication part. But it's something that we've been thinking about.
Okay, thank you.
Okay, so Bala, please continue the comments.
Yeah, no, I see you all in 2 weeks on Tuesday, not on Wednesday. This was a change to accommodate a holiday in Europe.